Our first speaker, Haoran Yu, is a PhD student in the ECE, Electrical and Computer Engineering Department at Rice University. His research interests include finding efficient methods for deep neural network training and inference. He's going to describe his work on ShiftAddNet, a hardware-inspired deep network.
Sure, then we'll start presentation. So hello everyone, this is Haoran Yu from Rice University, and I'm a third-year PhD student under the supervision of Professor Ian Lin. And today I'm very excited to present our work, ShiftAddNet, which is accepted by NeuralNIPS 2020. And the background of this work is that deep neural networks have become more and more important since they can achieve state-of-the-art performance over various tasks. The good performance attributes to two aspects: the large amount of available training data and the explosive computing power. However, these two aspects push a challenge for DNN training and inference. That is the prohibitive computational and time costs. For example, training a medium-scale deep neural network, ResNet 50, require 10 to the power of 18 floating point operations or flops, which is around 2 weeks when using a SOTA NVIDIA M40 GPU to train. Second, DNN training has raised pressing environmental concerns. For instance, the carbon emission of training one deep neural network can be as high as one American car's lifelong emission. Therefore, efficient DNN training and inference has become a very important research problem to solve those challenges. The bottleneck of efficient deep neural network is the massive multiplications, as indicated by the huge amounts of training flops. And there are opportunities to alleviate such inefficiency. Specifically, the costly multiplication can be represented by bitwise shift and add. And here we measure the unit energy and show the comparison between multiplication, add, and shift in terms of different precisions and platforms. We see that shift and add saves up to 196 times computational cost over multiplications. Based on such opportunity, we further hypothesize that leveraging the shift and add idea from the hardware field, we can redesign the DNN architecture, which should be naturally hardware-friendly. And here, we show the overall structure of the proposed ShiftAddNet. In general, we replaced the original convolutions with the cascaded shift layer and add layer. In such layers, all the multiplication among weight, activation, and gradient will become shift and add operations respectively. And there are great benefits for integrating those two weak players. First, ShiftAddNet can improve the expressiveness over shift-only networks because bit shift can only represent power of 2 multiplication, while addition after shift helps the full expressiveness. For example, if we want to map the input 2 to output none and only use bit shift, then we can left shift 2 bits to get the output 8. But output 8 is not what we expected. We need further add 1 to get the exactly outcome none. So adding add after shift can help the full expressiveness. And also, bit shift are more parameter efficient than addition. Let's take the same example. If we want to map the input 2 to output none and only use the addition, then we need to add 7. But if we first use bit shift by 2 bits, we only need to add 1 so that it's more parameter efficient. And also, adding such shift before the addition layer can improve the robustness, which will be demonstrated by the following experiments. And next, we notice that the shift and add naturally corresponds to coarse and fine-grained input manipulations. Benefit from such finer granularity control, we find that the coarse-grained shift layer can be fixed during the training and can also be further pruned. That can lead to more aggressive training and inference cost savings. And based on such observation, we propose the ShiftAddNet variant with fixed shift weights and shift layers. And then we evaluate the proposed ShiftAddNet across three models, the ResNet20, VGG19, and DCNN6 datasets, including the CIFAR10, CIFAR100, and 4 IoT datasets, and benchmark against the three SOTA baselines, including AddNet, DeepShift, and multiplication-based deep neural networks. And in terms of the achieved accuracy and the total training energy cost, note that the energy cost is measured by the SOTA FPGA board. Note that we also compare with multiplication-based deep neural networks and their comparable energy costs, that is 0.7 times or 1.3 times of the AddNet training costs. And overall, ShiftAddNet consistently outperform all the baselines, achieving up to 81% energy savings, while leading to comparable or even better accuracy. And we show some result samples in the below figures, where the proposed ShiftAddNet is denoted by the right triangles. We see that ShiftAddNet can achieve better accuracy and energy cost trade-offs than all the baselines, including the ConvNet, DeepShift, and the AddNet. And that comparison is consistent across a wide range of models, datasets, and precision types. Also, we compare the training trajectories to demonstrate the better convergence speeds of AddNet. As shown in the below figure, the red line denotes the proposed ShiftAddNet, while green line and blue lines are baselines, AddNet and DeepShift, respectively. The left figure shows the test accuracy versus the epoch, from which we see that ShiftAddNet indeed achieve faster convergence and higher final accuracy. And the right figure shows the test accuracy versus the training energy cost, from which we see that ShiftAddNet further saves over 13% energy efficiency than the baseline AddNet. Next, we compare ShiftAddNet with AddNet at different pruning ratios. The experiment results shows the great improved robustness for pruning. As we can see here, ShiftAddNet achieve higher accuracy and the same pruning ratios than the AddNet. And for demonstrating, we also visualize the corresponding weight distribution to validate such improved robustness. And the first line shows the weight distribution in AddNet, while the second line is the weight distribution in ShiftAddNet. We can see that the weight distribution maintains under high pruning ratios for ShiftAddNet, while collapse or shrink for the AddNet. This set of experiments validates the robustness of the proposed ShiftAddNet. And here we summarize the above contributions and the link for open source code. In summary, we for the first time proposed the hardware-inspired efficient deep neural network, ShiftAddNet. And we further found that the shift layer can be fixed during training. That can lead to more aggressive training and inference cost savings. And finally, we use extensive experiments to demonstrate the improved hardware efficiency and the robustness of the proposed ShiftAddNet. So I think that's all for today's presentation. Thanks for your attention. And do you have any questions?
Thank you, Haoran. Great talk.
Thanks.
We have one question to start off, which is how do you measure the training energy cost on an FPGA board?
Oh, that is a good question. Actually, the FPGA board, its resource is limited. And if we want to use it to measure the whole training process, it's infeasible. So in practice, we use the FPGA boards to measure the one epoch of the training and use such energy cost to scales to the whole training process. For example, if the energy cost for one epoch is 1 gigabyte G, and if we scale to the total training epochs, for example, 160 epochs, then the total energy cost will be 160 gigabytes G.
So the performance between the epochs is very similar. You don't get a lot of variance in the energy costs.
Yeah, actually, we have the variance. For example, here the range is from 25 to 80%. Actually, the lower bound is 25 is compared to the strongest baselines. Yeah, hope that can answer.
I mean, I guess I mean more when you say you measure one epoch and then you scale up, you just multiply it. The time, if you do measure multiple epochs, there's very little variance when you're doing the same type of analysis from one epoch to another.
Yes, they are variants.
Very similar.
Yeah,
Okay.
exactly. They are variants. Actually, we consider the variance when training one epoch and add such variance among the total training process, so that here we report the total range instead of the fixed numbers.
Okay. Great.
Yeah. Thanks for your question.
Michelle, are there more questions from the audience? I don't think I have a way of seeing that. Otherwise, I have some other questions I can ask. No. Okay, I will ask another question. So one of the questions I have is, what would it take for someone else to use this method? If somebody else, do they need special hardware? Do they just need, what do they need?
Yeah, actually, this is a good question. Actually, our model can be trained on the modern CPU or GPUs instead of the FPGA board. And here, we only use the FPGA board to measure the energy cost to back up our experiments. But for the practice, we can train the ShiftAddNet on the modern GPUs to demonstrate.
Okay, so if someone wants to get started, I think you had a link up earlier. They could go to that site and get the information they need.
Yeah, sure.
Okay.
So which slide do you mean?
You had a link at the end, I think, right there. Yeah, the open source code. Yeah. Another question I had was, this is in particular an optimization or a speed up for deep neural networks. Could this be applied to other types of machine learning, this approach?
Actually, this is a very good question, and our following work has extended the idea to natural language processing field, that is the transformer BERT models. Our ShiftAdd idea can also extend to such models that can bring a new perspective for doing the efficient NLP tasks.
Okay, great.
Yeah. Actually, I think one further direction is to develop some automatic search strategy to search for a hybrid model that includes both the multiplication and the shift and add. I believe that approach can achieve better accuracy and also to save the potential energy costs as compared to the modern deep neural networks.
Great. So a little bit of the best of both worlds. Wonderful. Thank you, Haoran.
Yeah, thanks.
If we don't have any more questions, I think we'll move on to our next speaker.
Sure. Then we'll stop sharing.
Okay, great. Thank you.
Thanks.
Okay.